Alright, well, let's start talking about processes and some system programming concepts. And if you've taken Engineering 270, you work with a PIC processor, and it's a little single chip microprocessor. It has some memory. You load instructions into the memory and it reads instructions, executes them, and it just keeps doing that all day long. If you played with an Arduino, little credit card sized processor, costs about $5. Same thing, it has a microcomputer, it has some memory, it reads instructions from the memory, it executes them, and that's what it does. And if you look at something like, a laptop, which can be running a web browser and monitoring incoming network traffic and telling me if I get a new email and doing some instant messaging updates, and it's monitoring the power level of the batteries and showing me there's 92%, and it's recording what I'm saying right now, and it's taking what's in the camera's view here and presenting it on the display, and it's doing all these different things at once, right? Which seems fundamentally different from something like a PIC processor or an Arduino that really just reads one instruction, executes, reads another instruction, executes, right? But the reality is, this computer is doing the same thing. It's really reading an instruction, executing, reading an instruction, executing. And it's doing these things one at a time. And as I say things like that, there's a little disclaimer, which is, most machines today have multiple cores, so they kind of have more than one CPU inside. So they actually do a few things simultaneously. But even with just a single core machine, right, go back about 5 years to a typical PC of the time, the CPU is only doing one thing at a time, even if it looks like it's doing multiple things. So if I hop on the server, and I probably lost my network connection because I was across campus. Alright, so there's only 2 people logged on the machine right now. Next Thursday there'll be probably 30 people logged on. But there's 2 people logged on the system right now. And PS is a command you can use in Unix to see what processes you currently have running. And so we've talked about some of this before, but we're going to go through it in more detail now. If I say PS, it shows me 2 lines of output. Okay. So this first column, PID, that's the process ID. So every process is identified internally by an integer. It's a 16-bit integer, so 0 to 65K. TTY tells me where this process is running from, and PTS is a pseudo terminal. It's not a physical piece of hardware connected to my CPU. It's a pretend terminal, and I happen to be logged in on PTS/1, pseudo terminal 1. Time tells me how long the command's been executing, and CMD is the name of the command. So just plain old PS shows me my processes. And you notice when I said PS now, I still have a process called bash and a process called PS. And the process ID of bash is 54967, but the process ID of PS has changed. It was 54979, now it's 55033. And if I do this again, it's 55036 and 37 and 38. And if I wait a few seconds, it may jump by more than 1. So this PS command does one thing, right? It prints out information about what processes are running, and then it exits. That command goes away. So if I say PS now, a new process is created to execute this command, which is why it has a new process ID. And if I do ps-l, I can get more information about processes. So, so user ID, that's an integer that says who owns this process. I'm user 1000 because I was the first ID created on the system. Process ID is still there. PPID is the parent process ID because most processes are created by other processes. In particular, this process that's executing the command PS has a parent process ID of 54967. That's my bash process. Because the program bash that's running right now, blinking cursor, if I type PS and hit enter, it will create a new process to execute that PS command. There's priorities associated with processes, and 80 is kind of a default priority. There's also a niceness associated with a process, and as a user, when you create a process, you can say be nice when you run this process, which means don't take as much CPU as you might. If you have something that you know is going to be really CPU intensive and you want to be nice to other people on the system, you can add a niceness value and it will devote less CPU to that process, and it slows the system down to a lesser degree. If you're a super user, you can have opposite nice value, which says give me more of the CPU, right? And so you can get more CPU time.
How do you change that value?
Nice. So there's a nice command. Lets you run a program with a modified niceness. So positive values give you a nicer state, so it takes less CPU time. Negative values get more CPU time. And you can specify a delta with a -n switch to bump up the niceness by a certain amount. And there's a note here, which is just something to note in general. Your shell may have its own version of nice. This is true of a lot of commands like echo. There's a version of echo that's built into bash. And when you say echo or you say nice, it may be running this program that's being described here, or it may be doing something as a built-in command for bash, right? And that's always a possibility. Right, you can also change the niceness once a process is running. You can re-nice it. All right, so we can see processes that are running right now. What it's showing me when I say PS are the processes associated with my current bash session, right? I can say PS-u nick, and that shows me all processes associated with the user ID nick. And I still get the bash and the PS down here, which are associated with sudo terminal 1. But I also get something called SSHD, something called STPAM, and something called systemd. And if I use the -L switch, I get more information about those, including parent IDs. So again, PS is created by 967, which is bash. That was created by process 54966, which is SSHD, right? Why is that SSHD? Because the way I created this process was from my own laptop. I said SSHD, nick at linuxengrcs.com. And I made a connection to a process on Linux called SSHD. And that process created a bash process. And that's what I'm sitting here, talking to with this blinking cursor. If I do ps-e, I can see every process on the system. And there's a lot of SSHs and lots of bashes and lots of SSHDs. Apache is web browser related, so this is the usual server that responds when a website tries to connect to this machine and ask for a web page. There's an Apache process. And there's daemons, like accounts daemon. These are things that sort of hang out in the background and respond to requests of different types. And there's all kinds of processes out here. So if I just do ps-e and pipe into word count, there's 135 processes sitting on this system. Right, and if you do ELF, you get more information about these processes. And we got more people logged in now. All right, so I'm sitting here. I do PS. I've got two processes: my current shell, which is bash, and my PS command. You can kill processes, but kill is a little bit of a misnomer. What you can do is you can send signals to processes. So signaling is a way that processes can communicate with one another. And you can send very simple signals, basically small integers. You can say, I'm talking to this process, I'm sending you a signal 5, or I'm sending you a signal 9, or a signal 1. And these signals have sort of conventional notions of what they mean. And a process can respond in different ways when it gets a signal. So if you look at the signal page, if we say kill-l, there's a list of the signals that we typically send to processes. So 6 bits worth: sig hup, sig int, sig quit, sig ill, sig trap, and so on. Sig hup used to be, back when you had a telephone line that you used to talk to a computer. When you were done with that, you would hang up the phone, right? And your process would get a sig hang up, HUP, sig hup, right? And that's typically what you use to say the communication has ended, and so we're going to log the system, log the person out of the system. Sig int is an interrupt, right? When you hit Control-C, you're trying to interrupt a process. Well, what you're doing is you're sending a particular type of signal to that process. Sig kill is a particular one. It says I want this process to go away, and unlike most of the other signals, you cannot choose to ignore a signal 9, a sig kill. Sig kill will kill a process no matter what. There's sig power, PWR, signal 30. That's related presumably to a power failure situation, or if the power starts to drop. Signal 11, sig seg v. That's usually related to some kind of segmentation issue. That's something like a seg fault. When your process tries to access a memory location that's not available, it will probably throw a signal. And the default behavior of that is to terminate your process and say, segmentation fault, and you're done. And so there's a kill command we can use from Linux, which basically says kill, and you put in the process ID of the process you're trying to signal. And you can specify dash followed by a number to say I want to signal this particular signal to this process. So if I say PS, I can say kill 54967. Well, I sent some default signal to this, but nothing seemed to happen. But if I kill -9 54967, my process gets killed and my connection closes. And now if I do a PS, my bash is back, but it's a different process ID. If I try to kill 55361, it'll say there's no such process. Even though that was the process ID of PS already exited. There was no process with that number. Now if I waited long enough, eventually another process will get recreated that uses that same ID, because there's only 65,000 IDs available. But they cycle sequentially, so it would take a while to get back to there. And I can try to kill I don't know, let's kill an Apache process. Process ID 48834. Right, and it'll tell me operation not permitted because I don't own that process and I'm not a super user. But you can kill processes that you own, and you can send them whatever signals you want. Okay, so if I want to create processes, just typing a command creates a process. And typically, once that process is running, it has the attention of standard in, right? Everything you type goes into that process. Everything that outputs comes to your standard out. And if I were to take a peek, that process is owned by Nick. Oh, that's weird. Hold on a second. Okay. So I'm logged in as a different user over here. I'm the user Nick. But if I do this PS ELF means show me all the processes in long format, and I search for Nick's, I can find these processes belonging to Nick. So there's the bash shell, right, that I'm sitting in. And that process, 356, created another process called VI test, right? That's this VI session that I'm sitting over here running. If I exit that and I look for processes owned by Nick again, right, the bash shell is still there, but the VI process is gone. Okay, so here's a little bash script that says enter your name, and my name is Nick, and it says hello Nick. All right. If I put an ampersand after a command, it will run that command, but it will do what we're calling running it in the background. So normally when this command runs, right, it's got the attention of standard in. Whatever I type here, right, rm star, is not being picked up by the shell. It's input to this script. And it says hello rm, and it interpreted the star as a file list. But if I say command with an ampersand at the end, that command starts to execute, but I come back to my bash prompt. Okay, so the script ran and it said enter your name, but if I say Nick, right, bash is picking that up. So I don't want to say rm star here. So with an ampersand, your command runs in the background. And if I do a PS, I can see that I have this thing called script sitting there running. So command ampersand says run in background. And I could say vi @, and that's running in the background now. And if I say PS, I've got my bash, I got script, I got vi, I got PS. And I'm also getting these messages that say stopped /script, stopped vi. So there's another command I can use called jobs, and jobs will show me the things that I've run with an ampersand. So if I say jobs, this says show commands run with an ampersand. The things you put in the background. So I've got my bash script that's running right now, that's listening to my standard in. I've got this thing called script, which was sitting in the background. I've got this thing called vi, which is sitting in the background. If I want to switch my attention to one of these things, I can bring that job to the foreground. And you do that with the foreground command, fg. And if I want to bring vi to the foreground, I can say fg%2. So fg %job_num says bring to the foreground. And being in the foreground means it's listening to standard in. So when I do this, I'm back in my vi session. If I'm currently sitting executing some command and I want to stop it, that's what Control Z does. This says stop a job. It's not the same as Control C, which terminates a job. Control Z will turn it back into being stopped. And if I say jobs, again, I can see vi and script. I can say foreground %1, and now my script is executing and it's waiting for me to type in my name. And if I Control Z that job stops again. So we can execute jobs in the background. We can bring them to the foreground if we want to interact with them by sending things through standard in and so on. And if it's in the foreground, we can stop it by Control Z-ing it. And we can also kill these. Right, so I can kill %2. But it doesn't actually kill it, because vi doesn't go away that easily. But if I kill -9 %2, that'll actually kill it. And now if I look at jobs, my vi is no longer there. And if I were to try to bring it into the foreground, there is no such job %2 anymore. And if you only have one job in the background, you can just say FG and it'll bring that job to the foreground. And then you can finish running that, and now there's no jobs sitting in the background. So let's sleep for 15 seconds and then say hello. And I can Control Z that, and that stops that job from running. It's in a stopped state right now. Right, it's still sitting there. I can say jobs, but it's not going to say hello in 15 seconds because it's not running. I can bring it into the foreground. And I don't know why it didn't say hello, but anyway, our 15 seconds expired. But if I wanted to run in the background, I can use the BG command. I don't think it's going to say hello. I need to make a script. Okay, let's do this. Okay, so delay is running in the background, and I'm sitting here and I can be typing commands and so on and so forth, and that script is running. So after 15 seconds it says hello, right, even if I'm doing something else, and then it exits, and so it tells me that it's done. If I Control Z it, it's sitting in a stopped state right now. And if I wait 15 seconds before I decide to start running it again, it should come back right away. The sleep will have expired, right, because 15 seconds have passed. It says hello and then it exits. Right, I can Control Z it. If I want it to continue running in the background, I can say BG, and it's just like saying delay with an ampersand. And now it's sitting here, and I can be inside VI doing whatever, and after 15 seconds the script will say hello. And then it'll exit. So from Bash we can create processes, we can manipulate processes, we can control processes in some pretty rudimentary ways, right? So PS is a good way to look at your processes. You can run things in the background by putting an ampersand behind them. You can background a current process by Control-Zing it to stop it and then saying BG to put it in the background. And you can say FG to bring it into the foreground. And that's useful sometimes if you have something that takes a long time. You want to run your analysis on War and Peace and it takes 5 minutes. And you got other things to do, you can run your command with an ampersand and it'll chow away in the background. And you can PS to see, how much time it's taken and so on and so forth. And still do other things. Sure does. Thank you. Alright, so this is burning up my CPU. And if I want to do other things, I can Control Z it. If I Control Z it like this, right, it's hanging out there, but it's not really doing a whole lot. If I run the top command on this other login, there's nothing really happening, right? There's 148 tasks, one of them is running, that's the top command, right? That's the only thing that's actually using CPU time. 146 of them are sleeping, one of them is stopped. But if I take this command and I say background %1, now it's actually running. And if I look at top, this burn command is taking 98.7% of the CPU. Right, so that's what this is telling you right here. And the load average up here is increasing. It went up to 0.34, 0.39, right? And this is an intensely CPU-bound process. It's not waiting for any I/O. It's not waiting for the disk to spin around so it can read something. It's really just executing assembly language instructions. And there's no delay in there. So the state says R, that means it's running. And it's taking about, 100% of the CPU. And I can make a copy of the executable called burn2, and I can start executing that. And now I got two processes taking up a lot of time, burn and burn2, and they're each getting about 50% of the CPU. So we've just discovered that this is a single core system. I pay $10 a month for it, so what do you expect? Right, and if I throw a third process out there, let's just run burn again in the background. All right, now they're going to split it 3 ways. And our load average is climbing. So that load average in the upper right, 1.4, when it gets to be, 1 or 2, you may start to notice a little bit of slowdown. When it gets to be 4 or 5, you'll probably be noticing a significant slowdown. When it gets to be 6 or 7, you're probably about to crash. So it's usually a pretty low number, and it's I think like 5 second, 15 second, 1 minute or something like that, 5-minute average. But normally we've got 150 tasks sitting out here, and their load average is 0.0 something. Right? The the operating system is very efficient about managing 100-some jobs without having to spend a lot of CPU cycles actually, doing anything except just waiting. But if you're CPU bound, you'll definitely notice it. So how do I get rid of this? Well, I could just kill %1, %2, and %3. I could foreground and Control C. There's a variety of ways. Let's just kill %3. So one of those burns goes away, and we're quickly back to almost 50% on those remaining jobs. I could foreground %1 and then Control C it, and so the other burn goes away, and we've just got burn2 running, and that's chewing up most of the CPU. And if I do jobs, there's job 2, and if I kill that, the CPU will go back to mostly idle, and our load average of 2.11 will start to drop, and the system quiets down. So I can run burn in the background. I'm on my laptop now. And burn's getting 100% of the CPU, 99.7. And I can run a few more copies of it. And I've got 3 copies of burn, and they're each claiming 98, 99% of the CPU. Right? I have multiple cores on this machine. And Kazam is still taking 40%. That's the screen recorder that's running. Cheese is displaying the document scanner. And I've got, other things hanging out in the background. If I run a 4th copy, they're not all getting 100% anymore. Some of them are getting 94, some of them are getting about 80. So let's run 8 copies. I've only got 7 copies. There's 8. And 8 copies are getting about 40-some%. So you can extrapolate from this. I've got 4 cores on my machine. And because I've got 8 processes that all want the CPU right at the same time, and there's not enough cores for them, they have to share the CPU. Right? And on the Linux server where we had a single core, if we had 3 copies of this running, they've got to share the CPU. Right? Because the CPU can only do one thing at a time, but we wanted to execute this program, execute that program. Right? Monitor for incoming email, monitor the network status, update the power display, and so on and so forth. So computers are really good at multitasking. Right? Basically, they do a little bit of this, a little bit of that, a little bit of this other thing. Right? Kazam, which is recording what's happening on the screen, does not need to record every single nanosecond of activity. It's making a video, which is maybe 30 frames per second. It really only needs to kind of snapshot 30 times a second. So there's a lot of downtime for Kazam, even though we're making something that looks like a continuous recording. And this time column shows you CPU time. And you can see Kazam has about 18 minutes of CPU time. Well, I started at 40 minutes ago at the starter class. Right? So it's half the time it's actually using the CPU, half the time it's not. And that kind of jives with the fact that it's got 40-some% of the CPU. So let's kill these things off. Still got a job there. Alright, those are all done. Kazam's the only thing taking CPU time now. And it's taking about, 50% of the CPU. Alright, so how does this work? How does one CPU manage to do 150 different things? This is part of what the operating system does for you. Yeah?
So I run like CPU intensive programs like a game or something.
Mm-hmm.
I noticed that some of them don't take advantage of the multiple cores.
Yeah, yeah.
How does that happen? Like, does something need to be programmed a certain way, or like?
Yeah, so depending on how it was written, right, it may be set up such that it can automatically use multiple cores, or it may have to actually be told, execute this on this core, execute that on that core. So like this program, right, this is going to run on one core, right, no matter what I do. But if I was really clever, right, I could split this into multiple pieces. Let's just say it's 1,000,000. I think it's 1,000,000. I could make that outer loop go from 0 to 500,000 and run that on one core, and then make another version of this that goes from 500,000 plus 1 to 1,000,000, run that on a second core. And then when both of these finish, I could add up the two sums that I got. right? And sometimes it's worth writing your code in a way that it can split up on multiple execution units. Some things like Java will take advantage of multiple cores, right? So every time you create a thread on Java, it will put it on a separate core if it's available. But it really depends on how the game is written, right? So if you anticipate being CPU intensive and you anticipate an environment where there's probably multiple resources available, you can set it up to execute on different cores, for example. We're not quite at the point where you can just write a piece of code and it'll figure out how to efficiently do that. But there's ways in which we're getting there, right? Things like threaded programming in Java being one example. I would think most of the game engines, though, would have pretty easy ways to do that, to let programmers take advantage of it. All right, so this is part of what the operating system does for you. If you take your code and convert it into assembly language and just load it into a PIC processor or an Arduino, right? This is what it will do. When you compile this and then you type in the program name, because we're sitting in an operating system, it doesn't simply take that code, load it into memory, and start executing it. Right? Because if it did that, that's all that would ever happen. And there's nothing in here which says if the control button is pressed and the C button is pressed, then exit. Right? Yet when this is running, if I press Control and C, it will exit the program. So all of this stuff is part of what's going on my Unix system right now. So here's the basic plan. You have a list of tasks. Right? They may not be sequential. You have a list of tasks that are trying to execute, that want CPU time. And you have this thing we'll just call the operating system, or the master control program. And when the operating system is running, it's using the CPU. Right? That's what the CPU is doing, is executing the code that makes up Linux or DOS or whatever your operating system is. But there's some sort of data structure. We'll learn data structures in winter. Think of an array that just contains, identifications of tasks that want the CPU. Well, the operating system looks in that array, and it looks at the first entry, and it says it's task 1, and its process ID is such and such. And somewhere in some big collection of memory, by using that process ID, it can find the code that goes along with this process. It can find the values of the variables that were being used by this process. It can figure out where standard out should go, where standard in should come from, and so on. And it will take all of that and it will load it into memory somewhere, and then it will say, start executing from that location in memory. And task 1 starts to run. And your operating system is not running right now. We're talking single core. Your operating system is not running anymore. Task 1 is running. But before that happened, what does it do? It sets up an alarm clock. This is like a timer in 270. It sets an alarm and it says, hey, after 1 millisecond, come and get me. So for the next millisecond, task 1 is running. A millisecond later, this alarm goes off, and the CPU goes back to executing where it was in the operating system's code. And the operating system checks the clock and says, oh, task 1 has had its millisecond. I'm going to put that aside for now. And it takes the current program memory, the values of registers and all that stuff, and throws it somewhere in memory. And then it goes down and it says, okay, I just did this task. Let's look at the next task, task 2. And it checks its PID, and it uses that to access all of its information, loads all that into memory, and then it says start executing that. And before it did that, it set a timer and said wake me up in a millisecond. Okay, that's fairly crazy sounding. That's a heck of a lot of work. But if your machine is running at a gigahertz, that's a billion things a second. That's a million things you can do in a millisecond. So doing those things that I just described, even though that's a lot of work, it's a pretty small amount of overhead compared to the amount of time that these tasks will actually get to run. And they may run for a millisecond, maybe 10 milliseconds. It's up to the operating system. And that can be tuned on many operating systems, depending on what kind of environment you're working in. So the operating system is this big program that starts running when you begin to boot the machine. And it's always hanging out there, but most of the time it's in the background. And a big part of what it's doing is it's just managing these tasks. And after the last task on this list is executed, right, next time it'll go back to this one. And then when task 2 is running, maybe task 2 exits. Maybe its main program hits that return statement and it goes away. Well, it takes it off this list. And even though that millisecond hasn't expired yet, right, this exits and it goes on to task 3, and then it'll go on to task 1, and then back to 3, and so on. And maybe while this is happening, somebody says, you know, PA5, and that creates a task 4 that goes into this list, what we call a queue. And then the next time task 3 uses up its quanta of time, now the OS will start executing task 4. And there's all kinds of scheduling strategies you can use for these things. And if you prioritize a job, if I set this thing to run with a higher priority, then maybe as it's going through the list, right, every 5 tasks it executes, it'll go back and give this thing a slice of time, even if it's not next in the list. And if something is niced, maybe it will skip it the first few times through. And there's all kinds of science and magic to coming up with a good scheduling system. And Linux does a pretty good job, which is why you can have a couple of hundred processes running and you can still type and you don't notice any delay in the response.
Do
All right.
those use ISRs?
Say what?
Do those use ISRs?
ISRs.
Shared service routines?
Yeah, so when that alarm clock goes off, that's going to basically be a software interrupt. And when you hit a key or you move your mouse or a packet comes in from the network, those will generate software interrupts. All right, so we're not going to go into operating system design. You can take courses in operating systems and learn the details of this. And you've got an operating system on your laptop, if you have a laptop running Linux, that you can explore, right? You can find the source code for it even, and you can modify it and recompile things. But we're not going to talk about that. We're going to talk about the mechanics of how these processes get created and how we interact with them. And we saw some ways to do this from Bash. What I want to start talking about on Monday is how we do this from C, because the operating system is written in C. So how does it create processes? How does it communicate with them? And so on and so forth. So we'll do that starting on Monday. All right, so have a good weekend, and I will see you next time.